This video is going to go over the properties of logarithms. So here are three basic properties that you're going to need. Well, actually four. The first one you're going to need to know is, or the first two are that log base a of 1, log base anything of 1 is always equal to 0, and log base anything of that base is always equal to 1. So, for instance, if I gave you log base 6 of 1, you know that'd be 0, because if you were to write that as an exponential function, you'd take whatever the base is, raise it to a power of whatever the logarithm's equal to, which in this case is 0, and set it equal to the input, which is 1. And you know that anything, it doesn't matter what the base is, because anything raised to a power of 0 is always equal to 1. Likewise, if I gave you log base 4 of 4, you know that's equal to 1, because if you were to write that as an exponential function, you'd take the base, which is 4, raise it to power of whatever it's equal to, which is 1, and set equal to whatever the input is, which is 4. You know 4 to the first power is always equal to 4. So it doesn't matter what the base is, as long as the base and the input are the same, the logarithm will always be equal to 1. Alright, here are a couple more properties that you'll need. If you have some number and you raise it to an exponent of log base whatever that number is of m, you'll always get the same thing. You always get whatever the input of the logarithm is. Likewise, if you take log base a of some number a raised to a power of r, you always just get the exponent. Because remember, logarithms and exponents are inverses of each other, so they always undo each other. So, the exponential and the logarithm will always undo each other. Likewise for here, so you're always left with what's left over, which would be m and r, because, like I said, logarithms and exponential functions undo each other. So here are a couple of examples. For example, if you have 2 raised to a power of log base 2 of pi, since the base of the exponential and the base of the logarithm are both 2, you're just left with pi. Likewise, if you have log base 0.2 of 0.2 raised to a power of negative square root of 2, you're just left with negative square root of 2. And final example, natural log of e raised to a power of k times t. Remember, the natural log and the exponential, the e, those are inverses of each other. Remember, because ln is just log base e, so that's log base e of e raised to k times t, so that just gives you k times t. Alright, here are some more properties of logarithms that you might need to know. If you have log base a of 2 things being multiplied on the inside, m times n, that's just equal to log base a of the first thing, m, plus log base a of the second thing, n. And if you're dividing, you can split them into separate logarithms and just subtract them. Alright, here are a couple more properties. If you have log base a of something raised to a power of r, you can just move the exponent out in front and multiply. Likewise, if you have some number a raised to a power of x, that's equivalent to raising to that number e, or that's the equivalent of rewriting it as that number e raised to a power of x times the natural log of a. So here's an example. Rewrite log base a of x times the square root of x plus 1 as a sum of logarithms. Now, if you notice, we're multiplying x by the square root of x squared plus 1, so that'd be log base a of x plus log base a of the square root of x squared plus 1. I wrote it down there because I ran out of room to write. So now, let's see if we can make this look any neater. We could rewrite this still. We could rewrite the square root as log base a of x plus 1/2, or log base a of x squared plus 1 raised to the power of 1/2. Getting ahead of myself. So now, since we have the second logarithm raised to an exponent, we can move it out in front. So we have log base a of x plus 1/2. Remember, move the exponent out in front. Log base a of x squared plus 1. Alright, here's another example. Rewrite this logarithm. Expand it into different logarithms. So you see how we're dividing those two things? We can separate them into separate logarithms, ln of x squared and natural log of x minus 1 raised to the third. And we could subtract those logarithms. But you see how we have an exponent with the logarithm? We can move it down in front, and that would give us ln of x squared minus 3 times the natural log of x minus 1. So here's another example. Rewrite this logarithm, meaning expand it into separate logarithms. So if we do that, see how we're dividing? We can start by dividing. So it would be log base a of the square root of x squared minus 1, we can rewrite as x squared plus 1 raised to the power of 1/2, minus log base a of, if we're multiplying these on the bottom, let's go ahead and just leave them alone for now. X cubed times x plus 1 raised to the 4th power. That's supposed to be a 3 right there. So now, you see this 1/2 right here that has an exponent. You can move that in front, so it'd be 1/2 times log base a of x squared minus 1 minus, it's open parentheses, see how you're multiplying these together? Well, you can expand those and add them. Log base a of x to the third plus log base a of x plus 1 raised to a power of 4. That's supposed to be a 4 right there. So, let's see if we can simplify this even further. Move the 4 down and distribute the negative in there, so you end up with... Alright, and this can be simplified to just 1/2 log base a of, that's supposed to be x squared plus 1. Now we distributed the minus, so that'd be minus log base a of x to the third. And since we distributed the minus over here and moved the 4 down, we'd also be subtracting minus 4 log base a of x plus 1. And this entire blue thing, if you can fit on one line, that'd be great. But that would be your answer. So here's more examples. Previously we were taking a single logarithm and breaking it into separate logarithms. Now we're going to take different logarithms and combine them into one. So for part A, if we want to combine it into one logarithm, see how we're adding the logarithms? That means we can write a single logarithm log base a and then multiply what's inside. 7 times 3, which would be log base a of 21. For part B, you have 2/3 ln of 8 minus ln of 5 squared minus 1. So, here you have an exponent, you can move it to the top, so that'd be natural log of 8 raised to the power of 2/3 minus ln of 5 squared minus 1. Let's see if we can simplify what's inside. Alright, remember, remember 8 to the 2/3 is just 4. And 5 squared is 25 minus 1 is 24. That'd be natural log of 24. So ln of 4 minus ln of 24. If we want to combine those, that'd be natural log of 4 over 24, which would be ln of 1 over 6. And since we have something being divided, we can expand it into separate logarithms. Ln of 1 minus ln of 6, since we're dividing. Ln of any log base anything of 1 is always equal to 0, so 0 minus ln of 6, which equals negative ln of 6. Alright, so for part C, log base A of x plus log base A of 9 plus log base A of x squared minus 1 minus log base A of 5. Since we're adding these three first, you could divide, or not divide, you can multiply the inputs together. So that's log base A of x times 9 times x squared minus 1, or you could do 9x times x squared plus 1. Now since we're subtracting log base A of 5, you could divide that by 5. Easy. That should be pretty simple.